All right. Hello, everyone. Welcome to our tutorial on natural language processing for information visualization. I'm really excited to be here, to be in person after a couple of years of virtual conference. So thanks again for coming so early in the morning here. And thanks also for those who have joined virtually from around the world. So good morning or good afternoon or good evening, depending on your location. So this tutorial is about natural language processing for information visualization, and it's a half-day tutorial. So we are gonna start now, and then we are gonna have some initial presentation till 10:15, and then we'll have a half an hour break. And then after we come back, we will have another hour and 15 minutes session before we end at noon. So just to introduce myself, my name is Inamul Haq. I'm an assistant professor at York University, and my research area is in natural language processing and information visualization. And with me, I have Shafiq Jyoti. He has joined virtually. He is the research director at Salesforce AI Research and also an associate professor at NTU Singapore. He's going to give more information about himself when he gives his part of the presentation. One thing I would like to mention here is that we have a website titled NLP4Vis.github.io. And we have posted our slides over there. So after the presentation, if you need it, you can always go there and download. Okay, so what this tutorial is about. So in this tutorial, we are going to talk about how we can utilize natural language processing techniques to solve various visualization-related tasks. So first, we are going to cover some of the basic concepts of NLP. And then after that, we are going to cover some state-of-the-art deep learning models, and that includes basic models like recurrent neural network, word-to-vec, as well as more advanced concepts like sequence-to-sequence models, attention mechanism, as well as the transformer-based models. We are going to talk about pre-training and fine-tuning of various language models such as BART and T5, which are quite popular now and widely used in various NLP applications. And then we are going to talk about what are the possible visualization tasks where we can apply all these advanced deep learning models and how that can help us in solving not only existing tasks, but also open up new areas of opportunities that are in the intersection of NLP and visualization. So, at the beginning, I would like to give a quick overview of why we need natural language processing for visualization and what are some example tasks, the visualization tasks that we can solve with natural language processing. So to answer that questions, we can first talk about the fact that language and vision, these are the two powerful communication channels that we possess as human. And so language and visualization try to take advantage of these two modalities of communication channels to improve the ability to explore data. And so here you can see some sample charts from various news sites like New York Times and Wall Street Journal. Each of these charts is trying to communicate some interesting patterns, trends, and outliers. But what we can also see is that each of these stories is also accompanied with text. And those textual data can further explain the insights from those charts. And that's how language and visualization can complement each other. While visualization is a very powerful tool for quickly understanding visual patterns, trends, and outliers, language can actually explain those patterns, trends, and outlier and provide additional context. So let's have a look at this, one of these sample visualizations to further illustrate this point. So this is a chart from New York Times. If you look at the raw data, it's very hard to find any interesting patterns or trends. But instead, if we visualize that in this chart, then some interesting patterns starts to emerge. So as you can see, the x-axis here represents the tax rate. Each circle here represents a company of a stock. The size of the circle represents the market capitalization. In other words, how much market cap this company has. And then the color also represents the effective tax rate. And as we start exploring this chart, we notice that some of these big dots at the left, this means that they are big companies, but they are paying low amount of taxes. Whereas if you look at the right side, there are some other companies, like these energy companies, they are paying a high amount of taxes, even though they are not big companies. So next, we also notice that the user can further explore this chart by splitting by different categories. So over here, we see that the user can explore the chart using different categories. I guess the play button is not working here. But what is interesting here is that for each of these different interesting insights, we have these textual elements that further provide context to all of these interesting phenomena and outliers. And so that's how textual explanation can help the complementary aspect of visualization. And then we also see that there is a search box at the top where the user can provide keyword to ask different simple queries, and then it highlights the result over there. So this particular visualization from New York Times illustrates how natural language and visualization can be complement to each other. While visualization is helping us to find visual patterns, the text is further exploring those, explaining those patterns, and then the text can be also used as a input modality where we provide search queries. So just to summarize, natural language and visualization can complement each other both in terms of input modality and output modality. In terms of output modality, we can use natural language processing to extract important data. For example, we can do topic modeling, we can do sentiment analysis, we can summarize large body of text, and we can also automatically generate text to illustrate different points about visualization. And then visualization, we can create visual picture of data, which can then help us by using our parallel processing abilities of our eyes to quickly figure out interesting patterns, trends, and outliers. Similarly, in the case of input modality, textual modality can help in expressing very complex information needs that would otherwise be very hard with like simple mouse-based interaction or direct manipulation-based interaction. And then similarly, you can still use mouse-based interactions and direct manipulation-based methods because that can also be very powerful for exploring visualization. So now, hopefully, we are convinced that NLP has lots of very, very interesting applications, and they can complement visualization in a very powerful way. So now let's think about what are some possible applications where we can apply natural language processing for visualization-related tasks. Well, there are various applications. One notable example is visual text analytics, which has been researched in the visualization community for quite a long time. Then we have the natural language interfaces for visualization, where the idea is to use natural language as an input modality. So, for example, you could build kind of a chatbot experience for visualization. So that's another area that has been immersed in the last few years. And a lot of research has been done in the last 5 years or so. And then we have automatic text generation or natural language generation, which can be used to explain things about visualizations automatically. So that's a very new area that has been kind of explored in the last few years, more recently. But then there are also other emerging applications like automatic visual storytelling generation, where we want to create a story from data, and that can combine both visualization and text. So again, there is a role of natural language processing there. And then finally, there are some applications like visualization recommendation systems and visualization retrieval systems, where we can use the textual content to improve those applications. So just to illustrate example of each of these tasks, for text analytics, there have been various text visualization techniques that have been proposed over decades, including very basic techniques like word cloud or tag cloud, where we take a document and then analyze the frequency of words and then visualize the frequency of those words, perhaps using the font size. There are some limitations of these techniques, and various techniques have been proposed to overcome those limitations, but I'm not going to go into the details of those techniques. Rather, there are some other applications that we could think about. For example, this is a visualization system called Tiara, where they have also introduced the time dimension in addition to the textual content. So they are trying to visualize how different topics in a large document collection is evolving over time. So each color strip is representing a topic. So you can see they have adopted the theme river metaphor, where each topic strip is represented and they are stacked on top of each other, and the height of each topic stream represents the strength of that topic at that particular time, so how much that topic has been discussed compared to other topics at that particular time. And then each topic is represented using the frequent keywords. So here they have applied topic modeling techniques. Now, visual text analytics have various platforms and domains where you could apply this, ranging from conversations like meetings, phone conversation, social media conversation, and interviews. Then beyond conversation, there could be monologues like lectures, radio news, broadcast news. And then beyond any speech, you have also various document collections like scientific documents, literature, and reviews. So in each of these domains, we have various research works that we have seen in the past few years that people have used different NLP techniques like topic modeling, sentiment analysis, and other techniques, and then augment that with visualization. And as I have mentioned, they have applied the text analytics techniques to solve various tasks like summarizing large document collection, understanding how people have expressed sentiment, applying different argument analysis, and also supporting fact-checking and rumor detection, and so on. Beyond visual text analytics, there has been this emerging area of natural language interface for visualization, where the idea is to introduce natural language as an input modality for visualization. So here is one example of how a possible natural language interface task. So we can see here we have a chart, and then people may ask various questions about this chart. For example, which year has the most divergent opinion about Brazil's economy? And then we see those who feel like the economy is going good versus bad. And we can see that in the most recent year, in 2015, the divergence was the most. So the answer is 2015 here. Similarly, if I ask what's the peak of the orange line, then we can see the orange line peak value is 87. So these are some natural language questions about chart, and the goal here is to answer those questions, usually with words. So this is from a recent paper that we have at the ACL conference. Here is another variation of the natural language interface, where instead of asking full-formed questions, you may ask some queries based on keywords. For example, you could ask like, large earthquake near California, and then the system needs to highlight all those cases that match these criteria and highlight here. And then you could also have follow-up queries like how about Texas, and then it could highlight the cases near Texas. Now, natural language interface has various benefits. For example, if we use natural language, then that can help people to express their information needs much more easily through language. For example, users who are not perhaps expert in data science and analytics, rather than trying to figure out complex visualization on how to interact with them, they might sometimes find it helpful to express their information needs with their lay language. And then because this is automatically computing the results for complex information needs, that can also lower the threshold of the analytical skills that they need for like data science, like statistical analysis and other various machine learning things that they have to do themselves. But instead, if the model can automatically do it for them, that can lower the required threshold of analytical skill. And of course, it can also reduce the cognitive burden because they don't have to do all this computation mentally, like summation, difference, multiplications. Instead, the model can do it for themselves. And then finally, last but not the least, it can greatly improve accessibility. For example, the blind people can ask questions about charts, and then they can get the answer. And similarly, other people, for example, those who have facing cognitive challenges and perhaps low verbal and visual working memory, other various challenges that they face, they can use this kind of technique to solve various computational tasks with visualization that would otherwise be hard for them. Okay, so text generation for visualization. This is again relatively new kind of topic. Even though there are some early works in early 2000, but really we have some works that have been done in the last few years on how we can automatically generate text to explain different insights from visualizations. For example, this is a chart from a data site called Statista, where it shows revenues of a company from different sources. And as you can see, we have this model that automatically generate a piece of text to explain the key insights from this chart. For example, it's saying the broadcasting is the largest source of revenue for Liverpool and so on. So this kind of textual explanation can be very helpful. For example, it can help reader in understanding certain data insights that otherwise they would have missed. It could also be helpful in suggesting various insights to the author who may be writing various data-driven articles. So it could also help them in writing various data-driven articles by suggesting pieces of text. Again, it could improve the chart accessibility because then people who are blind or have other challenges, they could hear the summary of the chart as they cannot see the chart. So they could at least get deeper insight about the chart compared to just presenting with raw data, because it's very hard to go over a large body of raw data to get insight from that. But instead, if we can present a textual summary, then that can greatly improve accessibility. And then finally, by generating text summary out of the chart, we can actually improve the retrieval and recommendation systems, because usually most of the charts online are in image format. So the search engines they usually focus on the visual content and the surrounding body of the text, but not the actual textual content of the chart. So if we can actually generate the data insights from those charts, that can also be used to index those charts and answer data-related questions. Automatic visual story generation is just another variation where we can use this automatic text generation in addition to visualization. So here is one system called Calliope, where they have generated a visual data story from a spreadsheet automatically, where we can see that they have a series of charts that illustrate various interesting data insights. But what we can notice is that in addition, they are also presenting with textual explanations that explains those insights. Of course, in this case, perhaps the insights are quite simple and simple statistics. And also the text is template-based, so it's kind of sounds sometimes boring because it perhaps looks similar most of the time. But of course, in the later part of the tutorial, we are going to discuss how we can generate more complex textual explanation that goes beyond this simple generation. So again, we can see that natural language can be used in automated data storytelling in a powerful way. Okay, finally, as we have mentioned, the visual retrieval and recommendation system can be greatly benefited from this kind of natural language processing. For example, this is a work on building a search engine where if the user provide a keyword like US election, then it's going to find out the charts that has textual contents, and rather than doing the exact match, it does apply semantic similarity. So that used word-to-vec similarity measure to figure out which visualizations are similar to this keyword query. So here we can see the application of NLP. Another example is visualization recommendation system. For example, this is a paper from 2020 Vis where the authors have applied the textual metadata of the visualization and used that to compute the similarity among the visualizations to create recommendations. All right, so far we have presented some example tasks and we have illustrated how natural language processing can be used to improve those visualization tasks. Now we are going to move towards our next part of the tutorial where we are going to dive deeper into the basics of NLP, and then we are going to follow that up with the description of how we can apply different state-of-the-art deep learning models in those NLP tasks. So for that part, I'm going to move over to the other presenter, Shafiq Jati, who is going to present this part about natural language processing techniques, the basics, as well as the deep learning models for NLP. Once we are done with that part, we are going to come back and talk about how we can then apply all those deep learning models to solve various visualization tasks. All right, so moving over to Shafiq Jati now.
Hello. So let me hear me well. Hello. Am I audible?
I think we can hear you. We can hear you. Can you hear us? Yep.
Okay. Yeah. So thanks, Anamal. So I'll be just let me make sure that I turn off my YouTube on. So you should be able to see my screen, and also as well as you should be able to hear me. So I'm going to take you through the NLP and also deep learning for NLP part. So again, just to introduce myself very briefly, so I'm currently a research director at Salesforce AI Research. and I'm mostly working on different NLP problems, and I'm also an associate prof at NTU Singapore, and I have been mostly working on deep learning and its applications to NLP problems. So this is how this section is gonna pan out. First, I'm gonna talk about NLP, what is NLP, and why deep learning for NLP now. And then we are gonna see some basic deep learning architecture in the form of feed-forward neural networks, and how we can use this to get word meanings or word vectors. And then we are going to see a bit more complex, which is recurrent neural networks, and see its applications in sequence level NLP tasks. And then we'll go for a break, and after coming from the break, we'll see more advanced architectures like transformers, again seeing the applications across all different NLP tasks. And finally, if time permits, we'll cover also the self-supervised learning, which is sort of very hot now. Okay. So without further ado, what is NLP? So in NLP, we study formalisms, models, algorithms that allow computers to perform some useful tasks. And these tasks usually involve knowledge about human language. Now let's see some examples of this kind of useful tasks. What tasks we are talking about here? So it could be conversational agents like Apple Siri or Amazon's Alexa or Microsoft's Cortana. And then it could be summarization. Let's say, please summarize my discussion with Sue about the NLP course, or what about or what people say about the new Nikon 5000 model, and so on. And then machine translation, like Google Translate, and then text generation, like data to text, like what Enamul has been talking about, how we can generate a description of a chart, or how we can do question answering over charts, and so on. And then question answering again, like from the free form text, and you have examples like IBM Watson, then document classification, like spam detection, news filtering, information extraction using knowledge graphs, which is actually one of the main components in Google search as well. Then speech, like automatic speech recognition, text-to-speech synthesis. And now also we have been witnessing a huge interest in multimodal applications like image to text, text to image, and so on. Now we can generate very photorealistic images using textual prompts, and so on. So there's really some influx of research going on in multimodal NLP in that sense. Okay, so that is sort of an idea about like what kind of task we are interested in NLP. Now let's zoom in the second part, like what kind of knowledge we are talking about here about human language. So when it comes to a language, actually it has different hierarchy of knowledge that we can think of. So if you're talking about the speech, then we need to know the phonetics and phonology, which relates to the sound. Then when it comes to the word, we need to talk about maybe the morphology or the tokenization. That means what is the suffix and what is the prefix, what is the root form of the word. So that is what we study in morphology. And then syntax, that means how the structure of the sentence is constructed. So this is basically the syntax or like how actually there are different kind of formalisms that describe the syntax. We have formalisms like phrase structure tree or constituency tree, where we try to describe the structure of a sentence in terms of phrases. Then we have dependency trees, where we have kind of relation between the words in terms of head and modifiers. So you have different formalisms to describe the construction process of a sentence. And in most cases, these are hierarchical structures. Then we have semantics, which deal with the meaning of the sentence. That means how we construct the meaning of a sentence to understand what the sentence is about. And then also the pragmatic use of language. That depends on the societal use, the demographic use of language. And finally, discourse and dialogue, when we want to deal with the phenomena that goes beyond one sentence, let's say anaphora or coherence and so on. So basically, we'll be talking about applications in along these different lines of language or different stages of language, so to say. So depending on the input, we'll be processing. Let's say you are trying to do a language understanding. So depending on the input, if it is a speech, you need to do maybe phonetic or phonological analysis, and then you'll be doing the other analysis like morphological analysis, syntactic analysis, semantic analysis, discourse analysis. And if you get the purely digital form of the text, then you'll be starting with maybe tokenization, then morphology, and so on. And so this is on the understanding side. And then on the generation side, you'll be going the opposite way, where you'll be planning the discourse, you'll be planning the meaning, then planning the sentence structure, then you'll be planning the word to use, and then you'll be realizing it. But we'll see in this particular tutorial that actually we'll not be doing all of these stages explicitly. Rather, we'll rely on the deep learning model to do this in its latent structure, in its latent hidden states, rather than doing this syntactic semantic analysis explicitly. We'll be mostly building end-to-end deep learning models. And that is how the current tradition is. So before I kind of talk about like what kind of model we want to see, and I just like to motivate why we are interested in deep learning from the cognitive perspective. So language is mostly a discrete or symbolic or categorical signal system. We have a concept and we represent this with a discrete word or tokens, so to say, like dog, cat, or pen. And the categorical symbols of a language can be encoded as a signal for communication, like we use sound, we use writing, we use gesture to sort of communicate these different concepts. However, human brains encoding appears to be continuous patterns of activation, and the symbols are actually transmitted by a continuous signal of sound and vision. So what it implicates that perhaps computers should also process the signal as a continuous signal for language rather than the discrete tokens or symbolic signal, or probably a mixture of these two. So that sort of brings us to the neural models, where we'll see that these linguistic concepts are actually will be expressed in terms of their distributed representation, which are actually vectors or continuous valued representation. So in this tutorial, we are going to see mostly deep neural models to talk about or to learn about different NLP tasks or to do different NLP tasks. So just a note here that traditionally, before 2012, it used to be models like finite state automata, Markov models, or graphical models, probabilistic graphical models that were the more kind of prominent approaches. But now it has already, most of them have been replaced by deep neural models, and they perform really well compared to those models. Okay, so now what is deep learning? So I've been talking about deep learning, but what is deep learning? So deep learning is a subfield of machine learning. So most traditional machine learning methods, they usually work well because of human designed representations or input features. And machine learning becomes mostly optimizing the features or the weights of these features. So let's consider maybe one task like NER. And here is an example of that. Let's say the sentence is Apple CEO Tim Cook introduces 2 new larger iPhones, a smartwatch at Cupertino Film Center event. So the task here is to identify that Apple is an organization, Tim Cook is a person, Cupertino is a location, Flynn Center is an organization, and so on. So what a previous approach would do is that it would try to come up with a list of features that would represent each word in terms of some features like what is the current word, what is the previous word of that word, what is the next word, what is the current word character engram, what is the part of a speech of this engram, of this current word, and so on. And then the machine learning task becomes learning the weight of these features, like which feature is more important. So the weight would determine how to combine these features and machine learning task becomes how to optimize these weights, how to get the best values for these weights. So instead, so basically the traditional machine learning is actually have two parts. One is you need to describe your data using features, and this often requires domain specifics or domain expertise, and often it requires PhD level expertise of the domain. Like you need to really understand your data to make sure that you describe the data in terms of right features. And then machine learning task becomes mostly optimizing the weights. So instead, what we are going to do in deep learning is that we'll be learning the representation or features of the input objects. So representation learning here attempts to automatically learn good features or representations in different layers of the models or different abstraction of features, okay, from very raw features to different abstract features. And we are going to do directly from end to end. So the input is going to be a raw input like sound, pixels, characters, and words. And the output can be, let's say, sentiment labels, or can be some self-supervised labels or some unsupervised labels like language modeling. And we'll be having multiple layers of neurons that will learn this kind of abstract features. And this will be done automatically by backpropagation or gradient backpropagation. So that we are going to talk about in a moment. Okay, so that is the main philosophy of deep learning, that we'll be learning representations at different layers of the model that would allow us to generalize well. Okay, so why deep learning? Why this kind of approach? That why we want to learn all the features rather than let human describe the features. Okay, so first of all, it provides a flexible representation and reasoning system. So manually designed features are often over-specified and incomplete due to our lack of knowledge, and also take a long time to design and validate. Now think about that, you have to do this for every task in hand, every domain, and every language that you want to do this. Okay? So this can be very expensive in that sense. On the other hand, learned features are easy to adapt and fast to learn. And deep learning, we'll see that it provides a very flexible, learnable framework for representing the world, like visual and linguistic information, and perform reasoning with that representation. And we'll see that deep learning can also learn in an unsupervised way, like from raw text or raw images. And it can also learn from where the supervision is available. Like when you say that this is a positive sentiment, is negative sentiment, or you say some kind of summaries like as a ground truth and so on. The second reason is that we need distributed or dense representation. Symbolic NLP systems turn out to be quite incredibly fragile because of their atomic symbolic representation. So traditionally, we have been working on the word tokens, but it turns out that these models, they don't kind of generalize well. And what we will see that the distributed or vector representation of words or phrases or sentences allow us to generalize better when we talk about, let's say, how the model performs on an unseen data. The third reason is the need for unsupervised or self-supervised learning. So in most practical setup, good traditional machine learning models require label training data. So that means they are mostly supervised learning. So here is a famous quote from Jeffrey Hinton, who says that actually, if we only rely on supervised data, then it's not possible. Like for humans, it is very limited amount of data. So actually, what he's arguing is that we need to somehow learn in an unsupervised way from the raw input without any supervision. So today's model like BART, Roberta, T5, Visual Language BART, DALL-E are actually changing the entire landscape of NLP, and they are all learned in an unsupervised way. The fourth reason is learning multiple levels of representation. So this also comes from mostly from the cognitive side of that our cortex system, they seem to have a general learning algorithm, but they have different hierarchy or different parts learning different information in our brain system, although they use the same learning algorithm. So this kind of tells that perhaps we need a hierarchical representation system where we can share the information I mean, different parts can share the information and they can process its own information that it is specialized for. Okay, so again, like in NLP now we see a lot of multitask learning, we see this like compositionality and multitask learning, like in the form of T5, where we try to do all sorts of tasks all together. So then the final question is why now? Why not before? Because these techniques have been there since in the 80s even. So the main reason is that around in the 2010, around in that like 2010 to 2015, and that time, the deep learning techniques started to outperform the traditional machine learning techniques, and mostly because large amounts of training data favors deep learning. And we now have faster machines and multi-core CPU, GPU, and TPUs that favor actually deep learning. And also on the modeling side, we have now better, more flexible learning of intermediate representations like transformers that we are going to see. And also we have effective end-to-end joint system learning, like we have, as I said, like a multitask learning that can learn, that can share from one task to another task. And we have effective learning methods for using context and transfer between tasks, and also better regularization and optimizations methods. So these are all kind of really recent advancement that kind of makes deep learning quite successful method in different tasks that has started in speech and vision, and now it is all over in NLP as well. So here's some recent breakthrough that I want to kind of talk about. One is, I think many of you know about AlphaFold from DeepMind, which actually solves kind of 50-year-old grand challenge in biology. The challenge is to kind of predict the 3D protein folding structure. And one of the main component of that innovation is actually transformer, which was actually first proposed for neural machine translation. Similarly, another one is DALL-E, which is the first sort of breakthrough in text to image. And now you have been seeing more from Google, from all these companies, that we can now generate very realistic images using a text prompt. But it all started with DALL-E. And again, here, the transformer architecture is one of the main things. Yeah. So now let's move on to the technical part of that. That we're going to talk about FFNs, or feed-forward neural networks, and odd vectors. So let me just see how I'm doing with the time. Yeah. Okay. Okay. So just a quick recap, and here I would assume that the audience knows a bit about the linear models like linear regression and logistic regression. So I'll not be spending time on that. Rather, I'll just do a quick recap of that. So in linear regression, our goal is to predict a continuous valued output. And the way that we define the model is actually a linear combination of the weights and the features. And then we try to minimize the mean squared error. And you can show that the optimization or the weights that we are trying to learn, we can express this in closed form like that. Or you could also use gradient-based methods to solve this MSE loss. In case of logistic regression, it's almost the same. That means the linear combination of the weights and the features, but now you also pass it through a sigmoid to get a probability distribution that tells us whether this is positive or negative or head or tail. So basically, again, this is the simple binary classification task using logistic regression, which takes the linear combination of the weights and the features, pass it through a sigmoid to get a probability distribution between 0 and 1. What is the probability that this is head or this is positive, or class 1. And then we can even generalize this to multi-class classification, where we have one set of weight for each class, and we need to now pass these linear combinations through a softmax function and normalize it to get a probability distribution for the classes. Let's say we have 5 classes. That means we'll have 5 different weight vectors, one for each of these classes, and we need to do the softmax to get a valid probability distribution that has sort of the nominator that is converting this linear combination to a positive value, and then the denominator is just summing up over all the classes to normalize these values between 0 and 1. Okay, so basically it is a multi-class classification, and the application can be let's say you are doing news classification or any classification that involves more than two classes. And you can train these models using stochastic gradient descent. And the main idea here is that you will initialize your weights or the parameters, and then you will gradually follow the gradient to find the best optimal place. So basically the gradient gives you the direction to find this the optimal point of the parameters, which in this case is W's. Okay. So basically it's an iterative algorithm that you will start from a random initialization, and iteratively you will be following the gradients with some learning rate eta, and ultimately if your loss surface is convex, then you'll find the best optimal or the global optimum. Otherwise you'll find some local optimum. Okay. So now let's move on to the neural networks. If you understand actually how logistic regression works, so that is actually one neuron in a neural network. Okay, so basically one neuron will take, let me see if I can somehow use my mouse here. Oh. So that I cannot use my mouse anyway. So, okay. So basically, one neuron will take the input, just like a logistic regression, x1, x2 up to xn, and then it will linearly combine it with the weights. So it will just multiply the feature with the weight, sum them up, pass it through a sigmoid kind of function, which is the activation function, and get an activated value. So this is exactly how a logistic regression works, right? So logistic regression uses a sigmoid function. Now, a neural network is actually is equivalent to running several logistic regressions at the same time. So here you can think of each of these green, each of these yellow dots or yellow circles are actually one logistic regression. So which is taking the inputs, combining it with the weights, and then passing it through some activation functions. Okay. So one thing is that on distinction here is that these are not random variables. So there is a deterministic relation between the input and the output here. There is no randomness here, or they are not probabilistic variables, so to say. I mean, typically, but you could also have apply variational methods to have kind of a probability distribution over these latent variables. Okay, so basically we can do multiple times like that. So we have one layer of logistic regression units, and then you could have another layer of logistic regression units, and so on. So you could have multi-layer neural network, and this is essentially a fit-for-all neural network. And the output layer is exactly the same as before. It can be a classification layer with maybe binary logistic regression, or it can be a softmax for multi-class or a regression layer, depending on what task you are trying to solve. Okay, so just to put it in with the vector notation here, so I'm just putting it here. Each of these yellow circles as like what operation goes through is basically one dot product operation with the input and one activation function that you apply to the output of that linear sum of the weight and the features. Okay, and you apply this activation function in the element-wise way. So each of so basically you apply sigmoid differently for each of these logistic regression units. It's not like it is taking the three I mean A1, A2, and A3 or 3Z here. It's just applying each of these in a individual way. Okay, so in case of like neural network, we often will be using these two terms. One is forward propagation, or these two information flow directions. One is forward propagation, which means that you'll be feeding the input to the model or the neural network, which in this case is x1, x2, x3, And then you'll be computing the prediction, and also when you are training, you'll be computing the loss or the optimization objective. Okay. And then the backpropagation is you'll be computing the gradient so that you can apply a stochastic gradient based optimization method so that you can take the next step in your optimization. So that is called backpropagation, where the gradients, which are also called errors, which actually measures how close you are to the ground truth objective or the ground truth labels, and you'll be backpropagating this to the intermediate layers so that you can fix it in the next iteration. Okay, so backpropagation is nothing but applying chain rule of gradients to compute the gradients in the intermediate layers or in the hidden layers. So now let's see how we can apply this kind of feed-forward neural network methods for word meaning, or trying to come up with semantics for the words. So what is word meaning actually in the first place? So the idea that that is represented by a word or phrase or any linguistic unit, right? So that is how, let's say, what is the idea that we want to express with a word or a phrase. Now the question is, how do we represent it in a computer? Now there's several ways to do that. The traditional way is to use denotational semantics, where the idea is to represent the meaning of a word in terms of other similar words or other related words. So we'll be using like lexical resources like OrdNet, where you represent the meaning of a word in terms of other words, like which are like synonyms or like hypernyms. Yeah. So that used to be the traditional approach. For example, here the word like good, you will, to represent its meaning, you'll be representing it with other similar words like goodness, maybe beneficial, maybe honorable, respectable, and so on. Okay. And also maybe other kind of related words like hypernyms and so on. But one problem with that is that OrdNet is sort of great as a lexical resource, but it misses the nuances. For example, proficient is listed as synonym for good. So this is only correct in some context. And also it misses the new meanings of the words like weak, badass, and nifty. So you have to update with new meanings, and it's a very tiresome job to update it frequently and impossible to keep up to date. And it's also very subjective. It depends on who is annotating it and who is writing it. And it requires a lot of human labor to create and adapt. And also, previously we are using mostly the discrete representation, which is like a symbolic representation or more like a bag of word representation, where we represent each word as a vector of 0, 1 values. So for example, here mortal would be represented by a vector of this, where the index of mortal would be 1, others would be 0. Similarly, hotel would be, the index of hotel would be 1, others would be 0. But now you can see in this representation, actually they are orthogonal, even though these two are related or synonyms in that sense. So these two vectors are orthogonal, that means independent, but even though in their meaning they are actually similar. So this is on kind of main problems with the discrete representation. So we could try to again use OrdNet's list of synonyms to get similarity, but we know that it's going to fail again because of all the incompleteness and all these issues. So instead, the main idea here, or the distributed representation, is to learn to encode similarity in the vectors themselves. And we'll be using the distributional semantics rather than denotational semantics. And which says that a word's meaning is given by the words that frequently appear close by. So there's a famous quote from J.R. Firth, which says that you shall know a word or the meaning of a word by the company it keeps. So when a word, let's say W, appears in a text, its context is the set of words that appear nearby, which is a fixed-sized window. And we'll be using this many contexts that this particular word appears in to build up the representation of that word or the meaning of that word or the vector for that word. So here's an example. Let's say we are interested in the word banking, and banking appears in this many context. We'll be using a fixed context to derive the representation or the vector representation for banking, or the meaning representation for banking, which is a vector. So which would look something like this, and which are also called word embeddings or word representations, and they are also called distributed representation because each of these dimension, they actually capture certain aspect of the word use. It can capture the grammar or the syntax of that word. It can capture some aspect of the meaning and so on. So basically, the meaning of the word is distributed across the dimensions. So that's why it is called also the distributed representations. So if you can also plot this, since we have a vector meaning representation, and we'll see that similar words will be situated together in the vector space, in the Euclidean space, in the two dimensions if we do dimension reduction. So, okay, so now let's see how we can actually come up with these kind of odd vectors. So the earliest method was actually a language model, but it was not actually proposed to, or it was not actually meant to come up with, or it was not actually proposed for a word embedding method. Rather, it was proposed to do language modeling. So what is language modeling? So language model takes a list of words or the context, let's say history. In this case, the example is the students opened there, and it will try to attempt to predict or it will predict the next word that follows them. So basically, it will try to define a probability distribution over the next, over the vocabulary, and this distribution should give what should be the next word. So the students open their books, the students open their laptops, the students open their exams or minds, and so on. And so here's the example of the first deep learning model. So I'll just use here. So how it works is that, so let's say we have the context here, the students open there, so this is the input, and then each of these words will be represented by their word embeddings or vector representation. So assume that we have a word embedding matrix, which is the size of that embedding matrix would be the size of the vocabulary times the dimension for each word. So then, given a word, the first operation that you will do is the lookup operation to get the word embeddings or the vector representation of that word. Now, once you have that word, we have the input in my deep neural network. Now I can pass it through a feed-forward neural network. So this is just one hidden layer that is taking this input, just multiplying it with this weight, and get each of these neurons in the hidden layer, and then pass it through another layer this is the output layer, and here is basically a softmax layer that will predict the probability distribution or a multi-class classification or softmax that will define a probability distribution over the vocabulary items for the next word. Okay, so whether this is books or this is laptops. So this is immediately applying what we have seen so far, like a feed-forward neural network to do language modeling. Given the context, pass it through the hidden layers, get the activation in the hidden layers, and define the probability distribution in the output for the next token over the vocabulary. Okay. So this was proposed in 2003, although it was meant to do only language modeling rather than learning these odd vectors, but it was a byproduct for that model. Okay. So basically how it works is that you have the input features. So basically have the two words. Let's say we have the two words thou shalt, and we'll be looking at, so this is the embedding matrix that will comprise all the embeddings for the word tokens in the vocabulary, and we'll first look up, get the vectors here, concatenate these vectors, pass it through one hidden layer, and define a softmax distribution or multi-class distribution over all the items in your vocabulary to get the probability distribution, that what is the probability that this is the next word is not, the next word is Aaron, the next word is Arthurs, and so on. Okay. So this is again the first model that was proposed, and that was essentially learning a language model, but as a byproduct, it was also learning this odd embedding matrix, which is essentially the odd vectors. Okay, but later on, because it has some hidden layers, it was back then it was not that kind of efficient, because neural networks it requires kind of a bit more compute if you have more hidden layers. So that's why later on what-to-bake methods came, which is more efficient, which has only input and output layers. So again, the main idea here is to we have a large corpus of text, and every word in a fixed vocabulary is represented by a vector, just like before. And then we'll be going through each position in the text, which will have a center word, and it will also have the context word, and we'll be using this context word and the center word to come up with the vector representation of these two words. Okay, so now let's see some example of that. So we have two different versions of what-to-bake. The first one is SIBO model, which is continuous backup word model. So basically what it does is that you have the context here, and given the previous two words and the next two words, we'll be predicting the middle word. Okay, so this is the representation of the word from the word embedding matrix, and we'll sum them up, get the representation here, and use a softmax to predict the next the word here in the middle word here. Okay, and in this way you'll be backpropagating the error in predicting this word, and you'll be learning the odd vectors for this odd embeddings, and that is how SIBO what-to-bake is. Now, the other version of the model is skipgram, which is the default what-to-bake model, which actually is the opposite one. Given the middle word, it will first again get the projection, that means the odd embeddings, which is just a lookup operation in the odd embedding matrix, get this and try to predict each of the context word individually. Okay, so basically you are getting here 4 different error signals in order to learn one odd vectors. So you're getting more signals than the SIBO model here. So again, just to show here, given that this is the middle word, what we are trying to do here is that we are representing this word with a distributed or vector representation in the odd embedding matrix, and then using that representation in a softmax to compute what is the next word, then what is this word, what is that word, and so on. So we are essentially defining this probability distribution for each of these neighboring words or the words in a context. Okay, so you can do it very simple. When you are implementing it, basically you go through each of this context, define what is the middle word, and that becomes your input, and the other word becomes your output, and you just try to, given this input, you try to predict the output word. Okay, so again, it's the same thing. Given this as input, you start with an untrained model, then you try to predict what is the next word, and you know that this is the ground truth. You'll be computing the error, you'll be backpropagating through this model and learning the model or the odd embeddings. Okay, so basically compute the error, and you know that so this is the actual target, and this is our model prediction, and this is the gradient or error, and then which is actually the model prediction is given by the softmax. Then you get the error here, which is the gradient, and you'll be backpropagating this error so that you can train the or kind of update your odd embeddings, which is the only parameter here. Okay, so you'll be iteratively doing it. You'll be making better and better predictions to match the ground truth. Okay, so you'll just keep doing it, and when it converges, you have a trained odd embedding model. Okay, so let me see how I'm doing with the time. Yeah, maybe I can do a quick. So let me see if there is any question in the in the Slido at this point. No, there's no question. Is there any question on the chat? No. So maybe I can go ahead for another couple of minutes and then we'll stop for a break. Okay, so now so far what we have seen is that we sort of gave a very brief recap of linear models like linear regression and logistic regression, and then extended this into fit-for neural networks by including more hidden layers. And we showed that we can learn these models using backpropagation, which is essentially backpropagating the gradients and using these gradients to update in our learning algorithm like a stochastic gradient descent. And we have seen an application of this in learning odd vectors. So now we'll go ahead and introduce a new model, which is recurrent neural networks, which used to be the workhorse for NLP researchers or NLP applications in that sense. So again, we'll try to introduce recurrent neural networks with the task of language modeling. So again, I'll be using the language modeling as the task to introduce recurrent neural networks. So here the task is, again, the language model will take the history or the context, and given this context, it will try to predict the next word. So that is the job of a language model, and we use it in our daily life in Google search, and also when you are typing, the tool suggests you the next word, right? Now the question is how we can build this model, and we have already seen one model for that is actually the fit-for neural net. So again, just to formally define what language model is, so a language model will take the history, which is like this x1 to xt, and it will try to predict the next token. And this token, that means it's a probability distribution over the vocabulary. Okay. Now, once you have this kind of language model probabilities, then you can use that probabilities to compute the probability or the likelihood for the entire sequence. Okay. So basically, you can also use the language model to score a text, that how likely a text is given the model parameters. Okay, so you can score like how good your model is, or how let's say you are trying to do maybe essay scoring, or you're trying to do maybe authorship attribution. So for each author, you could have a language model, and you could use a language model to define like what is the probability that this text is written by this author. So again, you could use language modeling as a way to score text for a particular task. Okay, so as I mentioned that, so this was the first language modeling model that was proposed in 2003, which was using mostly a fit-for neural net. But you could say that this model is limited because it can only take a limited window size, or it can take only a limited context. So in this case, it's only 4 words. So we could not allow this model, or this model did not allow us to incorporate a larger context, because then it would explode in terms of the parameter space. Because here we'll be needing that many words to incorporate the input for all these words. Okay. So again, think about the fit-for neural nets. How it works is that for each of the input signals, you will need one weight in your hidden layer. Now, to support, let's say, another 2 word, and if each of these word is like 300 dimension or maybe 500 dimension, you would need again another, let's say, 500 and 500 words in your. So then it's kind of you are increasing the words, and if you don't have, let's say, huge amount of data, then you cannot learn those reliably. So you'll be overfitting that. So in some sense, this is one of the limitations of the fit-for neural nets, that it does not allow you a flexible or variable length input or context. So I'll probably stop with this limitation, and then I'll introduce recurrent neural networks to overcome these limitations of fit-for neural net. So obviously, this is an improvement over the traditional n-gram-based language model where you just count. So there is no sparsity problem, and we don't need to store the n-gram. So this is even non-parametric. So this is parametric model. But the problems still remain with this approach is that the window size is too small, and window can never be large enough because language, the uses of words can depend on even something that happened maybe 2000, maybe 200 words before or something like that. So ideally, we would need an architecture that would allow us, in theory, to consider unlimited kind of context in that sense. And here, another thing is that each input vector is multiplied by a completely defined weight. So there's no symmetry by the way that we process the input. So one thing that we did not introduce is the convolutional neural network. But again, convolutional neural network is not suitable for variable length sequences. So we actually need an architecture that can process any variable length input. So let me see now how good you're doing. So I think we can take a break now. Enamal, is this the right time to do so?
Yeah, I think we need some coffee now and then come again after a half an hour. So let's take a quick break, and once we come back, we are gonna continue discussion on the deep learning methods for natural language processing, including the sequence-to-sequence models, more recent transformer-based models like BART and T5 and other exciting stuffs that are happening in the natural language processing field. So let's take a break and come back in half an hour. Thanks, everyone.